In this video, we are going to finish up the topics from chapter 2. The first thing that we are going to talk about is titration curves. Understand that the properties of acids and bases are actually very useful when it comes to biochemistry. Specifically, if we think about it, a titration, which is something that we have seen previously in other chemistry courses, it is basically an experiment in which a measured amount of base are added to a measured amount of acid. You may be thinking, how is this relevant in biochemistry? As we're going to see in the next chapter, amino acids, which is the subunit present in proteins, actually have these properties. So at this point, what I want to do is just introduce the components of a titration curve, which is the way in which we illustrate a titration experiment. As you can see illustrated in the right side of the, on the left side of the slide, we have a specific titration curve. This titration curve is going to be the titration experiment specifically for acetic acid being titrated with sodium hydroxide. So overall, I'm going to write on the top corner of the slide the acid-base reaction that it is occurring. So in this titration experiment, we're going to have acetic acid, which has the chemical formula CH3COOH. And when we combine it with sodium hydroxide, what we are going to be forming is sodium acetate and water. So overall, in this titration experiment, understand that what happens is that I'm just going to use my highlighter tool. We're going to have acetic acid, which I am highlighting in yellow. And we are going to be adding to it equivalence. So you can see I did it with the check mark of the NaOH. So the equivalence is basically how much NaOH we're adding to the system. So understand that as the experiment proceeds, there are certain regions that we need to pay attention to. So the first region that you can see here present in the second bullet point, and it is highlighted in that blue box, is specifically the buffering region. Buffers is something that is going to be explained in the next few slides. But for now, understand that that buffering region is a region where the pH of the solution remains constant. Now, it is called a region because it spreads for about 1 pH unit on either side of the pKa of the weak acid. Why is this important? Because this specific region, it is determined by the midpoint or the inflection point, which is specifically the area in the buffering region where we have equal amounts of concentration of the weak acid and its weak base. And as you can see, I highlighted that in a green area. Now, understand that as the titration keeps on occurring, so as we can increase the amount of base added, we are going to reach specifically a point that is called the equivalence point. Understand that the equivalence point is specifically where the acid in the system is exactly neutralized. So at that point, understand that the component of what we have in the solution is going to be the conjugate base of the system. So at that point, understand that the pH, once we have reached there, we're no longer under buffer conditions. So let's actually now understand what exactly is a buffer and how do they work. In section 2.5 of the textbook, as you can see, is where the explanation of buffers comes about. So buffers are going to be a solution that resists changes in pH. And understand that overall, the figure that we have here explains what happens where we have a solution that has a buffer and a solution that doesn't have a buffer. So let's first explore what happens when we do not have a buffer. So for example, let's say that you have a beaker with water, and with a pH meter, you decide to look at what is the pH of the system. As you can see, the pH of water is going to be 7.0. So let's say that to that beaker, we're going to add acid, because in that water, we are just adding a straight acid. What's going to happen is that that water is going to act as a base, and that acid is going to contribute a lot of protons. So that means that if we have a high concentration of protons, that's why we observe a drop in the pH value. Now, let's say that we have a brand new beaker, okay, of just water, and instead of adding acid, we add base. If we have base in the system, then understand what happens overall is that now we are reducing the amount of protons that are available. So overall, what that turns into is that we see an increase in the value of pH. And again, this is a system that we're just looking at what happens overall in water if we add acid or we add base. But now, if we have a buffer in the system, okay, this buffer is going to have components in it, and in a few moments I will explain how they actually work. That it doesn't matter if you add acid or you add base, the range of the pH is going to be very close to the pH of what we started with. Now, how do buffers actually work? Understand that even though there's many types of buffers, the one that is the most often used consists of equal amounts of a weak acid and its conjugate base. Okay, so what happens overall, and we go back to the example of acetic acid, that if we have our buffer, every time we specifically add bases or add base, in this case you can imagine sodium hydroxide, what is going to happen is at our weak acid, in this case acetic acid, will react with our base and is going to generate acetate and water. So you can imagine that overall, because we are consuming that acetic acid, the concentration of acetic acid is going to reduce. Since we are forming acetate, that is going to increase. Now, in the case that we have a buffer system, but then we are adding acids, then the conjugate base is the one that reacts with the incoming acid. So that's the case of what we have illustrated on the left side. If we have added acid in the system, what happens overall is that we have, in the case of this buffer with acetic acid, our acetate react with the acid and is going to form in turn more of our weak acid. So that's why overall, if acid is added to the system, we're going to see a decrease in the acetate because it is reacting with the incoming acid, and an increase on the weak acid that we have. So understand that that's how the buffer works in order to resist changes in pH. Now, if we go back to looking at our titration experiment that we expressed before, this is very important because overall we need to put into consideration that if we are doing a biochemical reaction, through the Henderson-Hasselback equation, we can actually determine all those different regions that we have for our titration. And if we have a particular compound, we can actually see what is going to be the buffer region that they contain. So here I'm bringing back the Henderson-Hasselback equation, and I'm utilizing as an example specifically the acetic acid titration that we have. So understand, I already explained that when it comes to a buffer, we would like specifically equal concentrations of our weak acid and our and its conjugate base. Now, if we think about it, utilizing the Henderson-Hasselback equation, we can actually pinpoint, for example, for acetic acid, what will be the pH where we have specifically equal concentrations of our conjugate base and the weak acid. And all we have to do for this is that if we utilize the Henderson-Hasselback equation, we're going to say the pH of my solution, taking into account the pKa of my acetic acid, as you can see that pKa is 4.7. If I have equal concentrations of my conjugate base, and we can utilize, a value of 1, just to make the number simple. So if I have equal concentration, if both concentrations are 1, you could use 0.1 over 0.1. Okay? You understand that because this log term is log base 10, log of 1 equals 0. So what happens at the inflection point, as I mentioned before, is that we have equal concentrations of our weak acid and the conjugate base. Okay? So that's where we have our ideal buffer. At this pH. Because in this case, understand that since the pH equals 4.7 is going to equal the pKa for our acid. Now, understand that the buffering region, okay, which establishes that is going to be 1 pH unit up and 1 pH unit down, comes from the idea that now these are going to be regions in which we have different concentrations of the weak acid and the conjugate base. Okay, so specifically at the pH of 3.76, which is this one, what we are assuming is that since that is going to be somewhere in this area that I circled, you can envision, because that is towards the beginning of our titration experiment, at that point, we will have specifically, if we compared the concentrations of acetic acid to acetate, there's going to be more acetic acid than acetate. Because at this point, we are just starting to add base. So the concentration of acetic acid is going to be higher. Once we are past that inflection point, meaning here where we are about our 5.76, understand that in that buffer system, we are going to have less concentration of the acetic acid compared to the acetate. And why is that important? Because then we are limited in this system, and this is just an explanation for acetic acid, that our buffer is going to be working best within these parameters. So it depends on what system it is needed for our enzyme, that we must select buffers that are going to be specifically in a region that are going to be within the range of what our enzyme requires. So, as I mentioned before, biochemical reactions, you need to be able to choose a buffer that will work specifically for your system. There are some criteria that needs to be met. First, you need a buffer that is a suitable pKa. You need specifically a buffer system that has no interference with the reaction of the assay, meaning that specifically the reagents, that weak acid and its conjugate base that are utilized, are not going to be reacting themselves with the biochemicals or even specifically with each other. They're going to be specifically targeting the acid and the bases that may be forming in the system. Now, they need to be specifically ionic strength, which means that this has to do with, again, the incoming acid or base that is in the system. It is important that your buffer does not create precipitations, because of precipitation, then it may aggregate. In other words, it may make a solid and the enzyme will be crashing, and then it's not going to be soluble in order to do the reaction. Some buffers need to be membrane permeable. It depends on how you're doing the experiment. And importantly, they need to be soluble, because if they're not soluble, they're not going to be in solution. So understand that this figure that we have on the left side of the slide is just illustrating specifically a different buffer system. This is going to be the titration specifically if we have phosphoric acid as a buffer system, but it's illustrating the same thing that I was mentioning before. Here we have the inflection point, and remember, the inflection point is where we have equal amounts of our weak acid, HA, and its conjugate base, A minus. And our buffer region is always going to be 1 pKa unit above, 1 pKa unit below our inflection point. That's going to be the buffer region. Now, how do we choose a buffer for biochemical reactions? Understand that there's a rule of thumb that when you are looking specifically at a buffer system, because all your buffer systems are given by a pKa unit, you need to select the buffer that the pKa should be about 1 more or 1 less unit from the pH of the reaction. So if you know, for example, that you need to run a reaction around pH 7, then you know that a good buffer for it will be, for example, MOPS, because the pKa is close to 7. So understand that when it comes to this, if you have a particular pH that you need for the reaction, you're going to be selecting buffers that are going to be around the same area of the pH, but it's just the pKa units. But again, it all comes from the idea that specifically when you have that pKa equal the pH of your reaction, you're going to have equal amounts of our weak acid and our conjugate base. So we're going to be in a good buffer region. Now, understand that buffers are actually present in the human body. And understand that these buffer systems is how we deal with acid that is generated in metabolic pathways. Here in this table, we have the different buffer systems that we have in the human body. They include the bicarbonate system, the phosphate system, the protein system. We have some that have hemoglobin. We have some present in plasma proteins. This is just illustrating some of the ones that we have. Understand that we have some that have ammonia. So as you can see, they're varied. And in addition to that, as you can see, there's a description of the site that they're in and what they actually deal with in the body. The one that I want to focus on right now is going to be the bicarbonate system, which is the one that it is present in our blood. So understand that blood pH must be maintained in order to have proper cellular homeostasis. And homeostasis is just a term that is utilized for having a system that works properly. Now, the pH of our blood is in between 7.35 and 7.45. So on average is 7.4. So any chemical reactions or biochemical reactions that need to happen in our blood, they need to be working properly. Those enzymes at pH 7.4. Now, understand that in that range, which is here in this green area, it is tightly controlled, okay, by the bicarbonate system, which is the buffer system that you see in the chemical reaction right here, okay? So if the pH extends away from that, as you can see, there are conditions that result from it. Here we have alkalosis, which means that the pH of the blood is higher than the 7.4. We also have acidosis, that it is where the pH drops lower than that 7.4. Understand that if the pH gets too high or too low, both of them result in death. Okay? So how do we regulate that pH? Well, in the bicarbonate system. So as you can see here in our bicarbonate system, what we have specifically is that it can be controlled by respiration. So to give you the overall view, here in the body where we have enzymes that if we have CO2 in the presence of water is going to make carbonic acid. That carbonic acid in turn, it can actually dissociate producing protons and hydrogen carbonate. Now, understand that this bicarbonate buffer system can be regulated by the lungs and the kidneys. So, what happens overall is that in this equilibrium system, we also have to be reminded of the Le Chatelier's principle. If we have any disturbances to this system, the equilibrium can be pushed towards the right or towards the left. So overall, what we see here, as you can see, this equilibrium arrows is what I'm referring to when I say, hey, this system is controlled by Le Chatelier's principle. So now we're going to actually look at applications of how this bicarbonate buffer system acts on the conditions I explained a few moments ago, acidosis and alkalosis. So let's look first at respiratory alkalosis. So in respiratory alkalosis, this is a system in which, as you can see, it is very serious. We have effects that affect the body by creating seizures, deep rapid breathing, hyperventilation, so on and so forth. So let's explain what makes the respiration or the respiratory system create an alkalosis, okay? So what happens overall, where we have a system that is in alkalosis, okay, is that, let's say, for example, that somebody, I'm just going to highlight it, is undergoing hyperventilation. So in hyperventilation, as you know, this person is breathing rapidly. And overall, during hyperventilation, because it's breathing in and out really rapidly, what is going to happen is that the person is going to reduce the levels of CO2 that are in the body. Remember, because these systems are in equilibrium, that's why we have those two arrows in the forward and the reverse direction. Because of the Le Chatelier's principle, we know if there's a reduction in CO2, the system has to make up for it. So what it does in turn is that it combines our proton with our hydrogen carbonate to make carbonic acid. Once carbonic acid is produced, then we have enzymes that will take the carbonic acid, create CO2 and water. So overall, what we see is that since we are combining the H plus with the hydrogen carbonate, we're going to see a reduction in the concentration of H plus. And because we have a reduction in the concentration of H plus, the system is called alkalosis because the pH, since we have less H plus, is going to increase the pH. That's where alkalosis come from. Now, I'm just going to erase this. Or actually, let me just leave it here. I'll just use a different color to explain acidosis. When it comes to acidosis, understand that this person, for example, is experiencing hypoventilation. So there are conditions in which you cannot breathe out the CO2 that you have in your body. So when that happens, understand that is happening overall is that if you cannot breathe out the CO2 in the body, then what you're doing is that you are increasing the CO2. If you're increasing the CO2, remember, based on Le Chatelier's principle, what we have is that then the equilibrium, the rate of the reaction in the forward direction is going to be increased, which means that if we are increasing the rate of the reaction in the forward direction, then our concentration of H plus is going to increase. So in the process of respiratory acidosis, because of the accumulation of CO2, we're going to see an increase in the concentration of H plus, and the condition is called acidosis because overall we see a decrease in the value of pH because of the increase in the concentration of H plus. And this concludes all the topics from chapter 2.